Okay, now we took out the circuit and we've put in a solenoid. A solenoid is just a set of wires that have been wrapped, this magnetic wire made out of copper. Now in this case, I've put these down here so that the students can see that it's one big circuit. I've also adjusted the solenoid. If you look here, there's a wire going this way showing the direction the coils are wrapped. But that's hard to see from the student's perspective, so I've added this paper clip here so that they can see the wires flowing this direction and the wires flowing this direction. That's just pure for demonstration purposes so that the students can see better. I'm going to hook this up so that I have the positive side here and the positive and the negative side here. Now this tells me if the current is flowing out this direction, it goes into the red. This should read positive. If current is flowing out the black lead, both galvanometers will read negative. This is important because we're going to find out that there will be an induced current and therefore an induced magnet inside the solenoid. We can't read that with a compass or something, but we can definitely figure out which way the current is flowing, which will prove to us the direction of the induced magnet. I now have a stack of magnets. Let's prove which side is north and which side is south. I have a compass that is pointing roughly north. When I go like this, notice it's the south side of the compass is pointing that direction. So this must be a north pole. Now if we look up on the board, we have 4 situations that we're going to go over. We're going to put a north pole in, read the ammeter. We're going to pull the north pole out, read the ammeter. South pole in, read the ammeter, south pole out, etc. And then we're going to derive experimentally what Lenz's law tells us. So let's start off with the north pole in. Okay, I'm about to put the north pole in, watching the galvanometer. Now, you saw it go to the north, you saw it go to the positive side. Let's mark this on the board. The galvanometer read positive, which means current is flowing into the positive side, which means the circuit being complete, it must go that direction. If we follow it from behind, it means all of the current on the front side of the solenoid is going this direction. Using the circular right-hand rule, which is for current flow in solenoids or wires, fingers from behind the solenoid, around the top, that means the induced magnet in the solenoid is to the right, or the north pole is on the right side. This is the north, and this is the south. Again, this is not something that we decided, this is something that we found experimentally. Now let's take the north out, back to the solenoid. I have to also notice that while the stack of magnets is in the solenoid, there is no induced current. That's very important. This only happens when there's a change of magnetism, not when there's magnetism inside the solenoid. So here I go. I'm going to pull this out. Ready? And it read negative. Let's go back to our diagram. If the meter reads negative, that means current is flowing into the negative side, following the circuit, out of the positive side, which means the current on the front of the solenoid is all flowing upwards. Now, one of the things that's helped the students this year is if you think about this as a hose and you put water into the hose, all the water will flow that direction. Using our right-hand rule, that side must be the induced magnet's north pole. Now, we'll take the souths. I turn around the stack of magnets, watching, ready, now. It read negative. Back up to the board. Again, if the solenoid reads negative, it means that the current flowed into the negative side, following the circuit, this direction, which means all of the current on the front of the solenoid flowed up this direction. Using our right-hand rule, up over the solenoid, our thumb points towards north. Now we take the south out of the solenoid. Watching, it read positive, which means current flowed into the into the positive side of the ammeter and out of the negative side. Again, from behind, all of the current in each of these is now flowing down the front. Fingers from behind, Down in the front, that's a North Pole. Now, we take a look at something very curious. Let's start again on our first situation over on the left-hand side. We see that we have two North Poles here, and two North Poles will repel. Here we see a north and a south will attract. Two south poles will repel. A north and a south will attract. In each of these cases, we try to put a north pole in, it opposes it with making a north pole towards the north pole that's trying to enter. I try to pull out the north pole. It makes a south pole, trying to keep it back in. I put a south pole in. It tries to make a south pole to repel it. I pull a south out. It tries to make a north pole to pull it back in. In each of these four cases, the induced magnetic field in the solenoid is opposing the change of magnetism. Now, when the magnet was just in the solenoid, there's no change, so there's no opposition, and there is no induced magnet, only when there's a change. This leads us to Lenz's law, which we have written in our physics kind of way. The induced current, I is current, just as we use in electricity. The induced current produces an induced magnetic field that opposes the change of magnetic field. Pause.